All right, so last time we started 3.4 and we got nearly finished. We're at the point at the end where we were looking at some word problems that involved multiplication and or division in pieces of them. And I believe that we're on example 3. Is that look correct to everyone? Okay. So example 3 says the following. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as the third, and there are twice as many in the second box as the first. How much does he have in each box? So these last 3 problems feel much like we're turning back into section for chapter 1 where we're doing problem solving, right? There's several different things you could do. Somebody suggest something. Okay, so where's 6 coming from? Okay, so that sounds awesome. Can I draw a picture for it first? Because you're picturing boxes, aren't you? I'm going to draw that picture. All right, so Brendan wants to have a box 1 and a box 2 and a box 3. And all of these boxes added together have a certain number of pennies, 4,000 some odd of them. I think I would change them into something else, but he's got lots of pennies. And so it says there are 3 times as many pennies in the first box as the third. So what can I do? Okay, so Haley suggests putting an X here and then a 3X here to represent 3 times as many. Does that sound reasonable? Okay, right? 3 times as many in the first box as in the third box. Does that work? Yes.
Yes, that works totally great. But I'm just curious if, like at an elementary level, how would you do that? Where they don't have variables.
You would probably use more of a guess and check kind of idea, which would be okay too. So we would pick a number in X and say, oh, there's, 100 pennies in the last box, and then we would triple it, and we could work from that perspective. Yes, you definitely could. And so this would be an algebraic way of doing this, but I guarantee algebra is coming at you guys younger than you realize. And so upper elementary school, they're encountering variables, and it's happening. But yes, if you were working at a younger level with the same kind of problem, maybe a smaller number, probably wouldn't have 4,000 in the number, just because we have to do a lot of guessing and checking to probably get this particular one to work out. You could use guess and check. All right, we have box 2. Twice as many in the second box as the first. So there's Brendan's 6X, right? Because if the first box has 3X and I want to double that, I'm going to get the 6X. Make sense? Now what am I going to do? What is X? It'd probably be a good idea for me to write down what I mean by X. Number of pennies in which box, Haley? Right. This is the number of pennies in box 3. Okay, so now what can I do? Excellent. All right, so Heather says I'm going to write 3X and 6X and X as a sum. And I'm going to have them equal 4,520. Sounds good? So what is 3X plus 6X plus X? Oh, I like 10. 10's very friendly, isn't it? So now I've got this. Now what? 5 by 10. So what is X? 452. It actually asked me how much does each box have, so I need to answer that question. I can start pretty quickly with box 3 has 452 pennies. Then what? Multiply by 3. Did you do that yet, Madison?
Yeah.
Okay, so box 1 is what you're working with. Has how many?
1,356.
Okay, good. I want to make sure I heard you right. This is pennies as well. And then someone else tell me what you do for box 2. Awesome. So I'll take my 1356 and I'll double it. And what do you get? Do you know that, Brendan?
1712 or 2712.
2712? Yeah, okay, good. And then we're finished. please make sure to answer the question that's asked. It's awfully easy to just get to the point where you have x equals 452 and you're done and move on. Make sure you answer what was asked. All right, last problem. All right. This is one of those smart kids in your class who comes up with something creative and they're going to frustrate you, okay? So I want you to sort of put your thinking cap on when they start doing this and just tell them some of the time you're going to have to say, let me take a look into that and I'll get back to you. Okay, but it's going to happen. There's going to be this kid in class to do this. And this one's going to say something like the following. A student observes that 39 plus 41 is 40 plus 40. You agree, right? We actually have a property, or not a property, but an algorithm where we did this. It was equal additions, where we took away something from one place and we added it to another place, and we had this happen. So this is a true thing. He asks if 39 times 41 is 40 times 40. So in other words, it's the same sort of a feeling of a property, if it is a property, actually hold for multiplication, right? First question is, how do you reply? Will it work? How do you know? What did you do, Haley? Okay, so you started working the problem, right? And actually you quit before you ever got finished because you saw it wasn't going to work. So let's actually work the problem to see what it would be so that we can tell the student, actually it doesn't work because this is what happened on this one. So let's start there. So Haley wants to tell him, no, it doesn't. And it doesn't, right? Because what is 39 times 41? What is it?
I don't know if I did it right.
Multiply, did you get some? 1599? Somebody said 1599, I did hear that. This one's 1599. And 40 times 40 is what? 1600. So it's actually awfully close though, isn't it? They're very close values. So if you really needed to multiply 39 and 41 and accuracy weren't all that important, this wouldn't be a bad approximation. Agreed? All right, so that's good. We've got something that's an approximation, but we're going to do another student that observes the same kind of a thing, but theirs is a little bit different. Another student observes that 39 times 41 is 40 times 40, but it's actually one less. That actually works, right? You can look back at the numbers we just saw and you can say, yep, I see that the student is correct on that. He also found out that 49 times 51 is 50 times 50 minus 1. And his question is, does this pattern continue? In other words, can you do this all the time? That's his question, right? Can you do this all the time? Does it always work? And how do you respond? Well, I want to show you an example. I don't expect you guys to come up with this on your own, but I want you to see that you actually have seen pieces of this at different points. And I want to show you how to pull it all together to show that it actually does work all the time. So, let's see the following. Consider the following. We're multiplying x times y. Okay? But the difference is that when I do this, what I'm supposed to be looking at them doing up here is they increased 1 by 1 and they decreased 1 by 1, didn't they? I mean, they end up being the same number, and I mean, I get that too, but they took 49 and they increased by 1, they took 51 and they decreased by 1. So I want to try that with just a general x and y and see what happens. Because even though you're not going to particularly show this kind of a reasoning to the child, if you really want to know if it always happens, you've got to do something better than just try a whole bunch of examples and say, yeah, I think so. Right? Because we've already established the fact that if you try lots of examples, there may be one example you didn't try that doesn't work. Agreed? Right? 0 divided by 0 is not 1. We did that one last time. So let's increase the first one and decrease the second one. So the question is, will this always equal the numbers that we got right here minus 1? Does it always do that? Well, this right here, if I were to multiply it out, let's see what happens, right? So foiling, anyone? You guys know what I'm talking about? So if I were to multiply the first two terms together, I'd get x times y. The outside terms, I'd get minus x. The inside term, I would get plus y. And the last term, I would get minus 1. And if the x and the y were the same, it looks like this might actually stand a shot. And I want to show you an easier way of dealing with it, because a lot of times people will bring in the x and the y like I just did, and they think, well, I'm just going to take two numbers and see if this works. Well, let's do a little bit more specific, because notice what kinds of two numbers they keep picking. What's special about the numbers the student keeps picking? What's 0? Well, we changed them into something that's a 0, but it's actually a little bit even better than that. They're both one away from, they are, but we can actually be a little bit more general than that. Notice the numbers that they're picking are actually 2 away from each other, aren't they? So I know it's really happy to see, you know, the 40 and the 50, because I like multiplying by tens as much as anybody, and that's great. You get zeros in there. But what we're about to show you actually will be more helpful to think of is if you notice that they're 2 apart. That is, if you decrease 1 by 1 and increase 1 by 1, you end up with the same number in the middle. That's the key. Okay, the key is that they have to happen to be the same number in the middle. So let's consider it like this. Well, you know what, let me write that down in a minute. We'll do that in a minute. So let's say that we've got one number and we've got one number that's 1 more than it. Or is it 2 more than it? Okay, just that. They're 2 apart. Whatever one number is, the other one's 2 more. So if you give me 36, I can do 36 and 38. This property is going to work. That's what we're questioning. So the question is whether or not I can decrease one of them and increase the other. So let's increase the first one, which would be x plus 1, and decrease the second one, and what does x plus 2 turn into? X plus 1. And let's multiply that out. So what happens when I multiply x plus 1 times x plus 1? What I was trying to do up here before. X squared plus 2x plus 1. Let's multiply this one out of here, okay? When we actually multiply the number out. What happens when I multiply x times x plus 2? Those results look very familiar, or very similar, I should say. What's the difference? The second one's exactly 1 more than the first one, isn't it? So if I take that result down here, this idea of taking 1 less and 1 more, I'm going to be exactly 1 off when I do that. And that's exactly how much the student was off up here, wasn't it? They were exactly 1 off. So this is exactly 1 more than the previous multiplication. Hence, if I subtracted 1 from it, I'd have the same thing, wouldn't I? And that's exactly what the students are doing up here. They're subtracting 1 off and they're getting exactly the result they wanted. Because it happened to be friendlier to multiply 40 times 40 than 39 times 21. Right? So the answer is actually yes, under the condition that they're actually the 2 apart that the student keeps doing. As friendly as it is that they're actually 1 apart from a number that's a power of, or a multiple of 10, and I like that too, that's actually not important. Like I said, I could choose 36 and 38 and it'd be okay. I don't like 35 times 35 any friendlier, but it would be okay and it would work. So this works. Whenever the factors, that's what those are called, the factors are 2 apart. Or you could say they differ by 2. And this is exactly what this shows. When the factors differ by 2, that is, one of them is 2 more than the other one, you can in fact increase 1 and decrease 1. And when you do that, the result will be exactly 1 more than it was previously. And if you subtracted 1, they'd be the same. Okay? Now, one of the cool things is that you guys have access to things that teachers before your time didn't have access to. So a student comes up to you and they say crazy things like this. Besides emailing me and saying, my student said something crazy, are they right? You could actually Google that and see, does this always work, right? And you would likely come across something that looks like this. A yes or a no, and then it's going to give you some kind of justification. You need to be able to read through that and make sense of it. You have to be able to come up with it on your own? No, not necessarily. You should be able to read through that and say, oh, they increased this one, they decreased that one, if they're two apart, this is reasonable. Hopefully they've got enough verbiage along there with them that you can read through that and make sense. That's the idea. Okay? All right.